This last video is going to go over all the different types of nuclear reactions, maybe split into a couple. We'll see how long it takes. So from before, all right, we saw that there's three different types of ionizing radiation you have to know about: alpha, beta, and gamma. An alpha particle is a helium nucleus. It's 2 protons and 2 neutrons. And a beta particle is an electron and positron, depends on which type. And a gamma particle is just a very, very high energy photon. All right. So this chart tells you a little bit about them. Okay. The smaller that they get, you can think of. All right. The more material is needed to absorb it. All right. The ionizing effect becomes stronger, all right, as you go towards the alpha. The reason is that the alpha particles have such a large amount of charge; they're very good at ionizing things. All right, but yeah, that's pretty much it as far as like the information that you need to know. And also, we can determine what type of radiation it is by sending it through a magnetic and electric field, and depending on which way it bends, we know it's got a positive charge with an alpha particle, negative charge with a beta particle, or technically positive charge with positron for beta plus, and for gamma radiation is completely unaffected. All right. So just some little facts about these three different types of radiation you should read over. Okay. But the big idea here for alpha radiation, all right, we have an alpha particle. It is a helium nucleus, and so what I was saying before is that you have these elements that are unstable, so they're going to naturally decay, and there's a probability that they may decay in a few different modes, but the most likely sequence for these decays, all right, have been measured. Oftentimes we have like little charts that show this. I think there's a chart in your book that shows the possible sequence of decays of radioactive elements, and they're always trying to get back to a non-radioactive element, and typically they end up following alpha and beta decays until they get to lead, which is the first element that has a non-radioactive isotope that is naturally occurring. Okay, so we have an example reaction here. We have radium-226 decaying to radon-222. And we got to make sure that we keep track the bookkeeping here with these numbers. Okay, we have the atomic number here at the bottom, all right, the mass number here at the top, and that all adds up in the end. Okay, so what ends up happening, okay, is we have this energy that's released. What it actually is the same concept that we used for calculating binding energy here. We actually have a little bit of the mass of the radium nucleus being released just as energy. And that energy is kinetic energy of the daughter particles, or of the products, okay? And the kinetic energy comes from the rest mass of the parent particle, and all right, the release of energy in nuclear reactions, again, like I said, is in the form, is in the kinetic energy of the daughter particles. Okay, so it's that thermal energy really that you can think of being released. All right, so the result here, okay, is that we have alpha decay. Helping the nucleus to achieve a more stable configuration, all right, with higher binding energy per nucleon, all right, since that energy has then been released, all right. So let me give you that right here. Okay, the nucleus is more stable. Okay, energy has been released. And this now means there is a higher binding energy per nucleon. In other words, more energy has been released per nucleon now, all right, for it to have this configuration. So we can do this problem quite easily. The example reaction from above, if you guys want to include this, okay, to actually calculate the energy released here. The way that we do this, right, is that we're looking for that mass defect, that change in mass. It's just going to be equal to mass of the radium nucleus, all right, minus the mass of the radon, minus minus the mass of the alpha particle. And if you look up all of these, okay, the mass of the radium is 226.025402 U. Mass of the radon is going to be 222.017571 unified atomic mass units, okay? And the mass of the alpha particle, that's what this little fish thing is the Greek letter alpha, is this. Alright, so we find that the mass defect ends up being equal to this, and that is released as, now if we do the conversion factor of the energy, then it becomes 4.87 mega electron volts. Okay? So that's how much energy has been released in that reaction. Alright? Oh, I actually already did that. Just there, so move on here. Okay. For beta particles, alright? For beta decay, you have two different types. You have beta minus decay and beta plus. With beta minus, you are emitting an electron, and for beta plus, you're emitting a positron. We haven't talked about antimatter. It is simply the reverse of matter, if you want to think of it that way, in terms of its charge and some of its other properties. So a positron is just an electron in terms of mass, if you want to think of it that way, but it has a positive charge. Okay. So there's something really, really interesting about beta decay. All right. Let's say that we have a radioactive isotope like carbon-14, which we have right here. Carbon-14 undergoes beta decay. All right. And if we consider it beforehand, okay, let's pretend like it doesn't have any velocity. Okay. So if it has no velocity, there's no kinetic energy, all right, and it has no momentum. And what happens is that after the decay, okay, we end up with both particles, okay, having a velocity, okay, and some amount of momentum. If one observes this graph, all right, that tells us the kinetic energy of the beta particles as they move away, okay, we know that there should be a maximum amount of kinetic energy that these particles have, all right? And we actually see that the number of beta particles with certain amounts of kinetic energy, all right, the majority of them are way before this maximum amount of kinetic energy that it can have. Now, you know, if we consider the fact that beforehand, and let me help you imagine this, okay? You know, you have a carbon atom that's completely stationary. Afterwards, okay, because this electron is so small, the beta particle is so small, depending, you know, whatever type it is, beta plus or beta minus, regardless, it's so small, okay, that it's going to not, there isn't going to be, this particle, this nitrogen particle is not going to have much velocity, okay? So we can figure out pretty much, all right, that this missing mass should end up as purely the kinetic energy of the entire beta particle, almost, okay? But what we actually end up seeing, okay, is, and that previous statement, sorry, is based on the conservation of momentum here, okay? But what we end up seeing is that these beta particles have mostly this kinetic energy that's at this level, all right? Some of them have it up to here, but none really have that maximum kinetic energy. And what we see is that there's a missing bit of energy in this. And this was a mystery for physicists, and so what they posited was that there is a particle, okay? So the conclusion here is that there's missing mass, and to them this meant there must be a particle that is not being detected. And what they realized that this particle must be neutral because they weren't able to detect it with their, their detectors. So they assumed that it was very small and uncharged. And so Enrico Fermi actually came up with the name, little neutral one, neutrino in Italian, to name this. Okay, so this is a very small, uncharged particle. Okay, and we use the symbol, I think, nu. It's like, looks like a V, one side's straight, the other is curved, kind of like this. And so this is our neutrino, and our antineutrino, there's a line over it, okay? think of an evil mustache, evil twin version. All right. And so what we see here, you notice that the range of energies here that beta particle can have is continuous. All right. And so what this tells us is that the spectrum, the energy spectrum of beta particles, all right, is unlike that of photons we've discussed so far, and they can have any value. All right. So quickly, let's talk about the difference here between these beta decays. All right, beta minus and beta plus decays. So for carbon 14 to decay into nitrogen 14, all right, you must have beta minus decay. And what this tells us, we have a proton, we have a neutron changing into a proton here, increasing the atomic number. In order for that to happen, okay, we need to emit an electron and an antineutrino along with whatever kinetic energy, okay? For beta plus decay, all right, what we end up having here is we have a proton turning into a neutron, so that atomic number decreases. And when that happens, you have to emit that positive charge that comes out as a positron, okay, with some mass. So, and the neutrino and some energy. So the general equations are here below, but you just need to know, when I think of the fact beta minus decay, if you're emitting an electron, that means you're losing negative charge, you must be increasing in positive charge in the nucleus. Same thing goes for beta plus decay, all right? So think about what's leaving. If that's negative charge that's leaving, all right, that must increase the positive that's in the nucleus, okay? That's just the way I remember it. All right, so gamma decay is this last piece here of ionizing radiation. A gamma particle is just a high energy photon, all right? And typically what you end up with, gamma decay occurs after an alpha or beta decay. It's just electromagnetic radiation, okay? And so this is, what you have here. This starred version of the atom, okay, basically tells us we have a nucleus in an excited state, okay? When it relaxes, it emits a photon. Okay, and that's pretty much it. So those are the three different types of ionizing radiation. So you've seen so far that the beta spectrum is continuous. Okay, there's a continuous set of energies at which beta decay can happen at, but alpha and gamma decay don't happen like this. Okay, we know gamma decay, any sort of electromagnetic radiation must be emitted in a discrete fashion. But this is also true for alpha particles, okay? What we see is only discrete energy levels, all right? If you actually look at, say a graph of alpha particle intensity, okay? I call it intensity of alpha particles. And actually, I was able to find a nice graph of this on Wikipedia. And you consider different sources, you get spikes at specific points, and that's it, in terms of whether or not that particle will be emitted at these energy levels. Okay, so that tells us that this is a discrete thing. Okay, it can only happen in certain places. So this is important. Okay, this discrete alpha spectra, it tells us, okay, and gamma spectra actually, this is on the previous page, that nuclei, not just electrons around the nuclei, but the nuclei themselves, they have discrete energy levels, just like we had with electrons. Okay, so alpha is discrete, continuous for beta, and discrete over here for gamma, all right? Okay, so I have an example here. I think I'm going to tackle this in the next slide, in the next video, all right? Yeah, when I do that, we'll talk about fission and fusion as well.